All right, so we're going to go over section 8.8. We're putting it in. Okay, so this is called linear programming for problems, and the concept here is just like the last example we did tonight on sketching an entire set of a system of inequalities. And what we're going to do is we are going to find the solution set for a optimization function. All right. So what we're going to do is we're going to sketch the region corresponding to the system of constraints. Okay, that's our system of inequalities. The points in the region or on the boundary are all possible solutions. We're going to look for the vertices of the region, the corners, if you will, because this is where you're going to either max out or min out your possible answer. So we're going to test the objective function at each vertex and select the values of the variable that optimizes the objective function. For a bounded region, both a minimum and maximum value will exist. Unbounded region will only have a solution at a vertex. So that's if our shading goes on continuously in one direction. I'm going to close everything off. It's easier that way. All right. So if we number our grid, every two squares count as ones because this is going to increase the size of our area so it's easier to graph. We have a maximum objective function. So we're looking for the x and the y coordinate on the vertex that gives us the biggest value. So x greater than or equal to 0, y greater than or equal to 0, as I mentioned, that cuts off quadrant 1. So we're completely graphing in quadrant 1. So we just have to graph these other two inequalities. So there's the red, there's the blue, like we did earlier. It cuts off quadrant 1. X plus 2y is less than or equal to 4. So we cover up the y term to find the x-intercept. We'll do this in purple, so x is equal to 4. We cover up the x to find the y. 2y equals 4, y is equal to 2. Connect that together. Test your origin. 0 plus 0 is 0, which is less than 4, so that's the direction we want to shade. And then we have x minus y is less than or equal to 1. Okay, so here we'll do this one in green. So finding the x-intercept, cover up the y. X is equal to 1. But you cover up the x, y is equal to negative 1, which is technically not on our graph. That's okay. We'll find our slope, or we can put this into y equals mx plus b form. You can add over the x, or excuse me, subtract over the x, and then you divide everybody by a negative 1. But when you divide with inequalities that are negative, you multiply or divide a negative with an inequality, you have to flip the inequality symbol. So we have a slope of 1, and you could have gotten that from the negative a over b. So a was 1, so that's negative 1. B is negative 1, so negative 1 over negative 1 is a positive 1. So we'll go up 1 unit to the right 1. There's that point, and we can draw our line. If you test the origin, 0 minus 0 is less than 1 is true. So if you think about this line continually going down to here, the origin is in your solution set. Or if you put it in y equals mx plus b form, we're saying y is greater than, we're shading above the line. So this solution set is my possible answers that will maximize my objective function. So we have to look at each corner. We're going to look at the point 0, 2, 2, 1, and 1, 0. And we're going to test them in the maximum, the objective function, to find the maximum value. So if we test 0, 2, 3 times 0 is 0, plus 2 times 2, that's 4. We test 2, 1, 3 times 2 is 6, plus 2 times 1 is 2, that's 8. And test 1 and 0, 3 times 1 is 3, 2 times 0 is 0, so that's a 3. The point 2, 1 is our solution. That gives us the biggest possible value in our objective function. So that's the point that maximizes the objective function. All right. Okay, so here, they give us a function, objective function, that we want to find the max and the min value. So again, x greater than or equal to 0, that's quadrant 1, so we're there, shading out. I'm not going to use any special colors. 2x plus 3y greater than or equal to 6, find your intercepts. To find the x-intercept, cover up the y, 2x equals 6, x is equal to 3. Find your y-intercept, cover up the x, 3y equals 6, y is equal to 2. So there's those 2 points. Draw your line. 0 plus 0 is 0. 0 is not greater than 6, so we don't want to shade towards the origin. We're shading upward this way. So let's see, 3x minus 15, or excuse me, 3x minus y is less than or equal to 15. We can find a point, cover up the y, x-intercept is at 5, 0, but you try to solve for y, that's negative 15. We don't have that down here. So your slope, opposite of a, negative 3, over b, negative 1, is 3 over 1. So we can go to 5, plot a point, there's our 5, and we can go up 3, right 1, plot a point. Up 3, right 1, plot a point, and keep plotting those points. And again, this line goes all the way down to negative 15, so here's the origin. And 0 minus 0 is 0, which is less than 15, so we want to shade towards the origin, so we're shading on this side of the line, if you can imagine that line continuing downward. Here, y-intercept is at 4, but x-intercept would be negative 4. Again, we don't have that, so you have the y-intercept at 0, 4. Opposite of a, opposite of negative 1 is positive 1 over 1, so we have a slope of 1. Start at 4, up 1, right 1, up 1, right 1, up 1, right 1, and continue to fill in the graph. Again, 0 plus 0 is less than 4. 0 is less than 4, and this red line would continue here. Your origin is below that red line, so we're shading in this direction, so everything appears to be in this region so far. Now, the last one, this one's kind of difficult because the 2 doesn't go into 27, the 5 doesn't go into 27, and converting this into y equals mx plus b is just going to give us a bunch of fractions. So here's a way we can cheat. All right? Find multiples of 2 and 5 that create the sum that is 27. Well, I know that 5 times 5 is 25, so if y were to be a 5, and 25 plus 2 is 27, so that means x is equal to 1, then this would be a point that's on that line. Excuse me. Then, taking opposite of a, negative, taking opposite of 2, that's negative 2, over b, 5, that's my slope. So I can go to 1, 5, that's this point right there, and go down 2, and to the right 5. 1, 2, 3, 4, 5, and that's this point. Connect that together. So 0 plus 0 is less than 27, so again, we're shading towards the origin. So all the arrows are pointing into this region. This is my solution region. So if we want to maximize and minimize, we need to test all these corners. So we have the 0.15, we have the 0.63, and those are the 2 I'm going to test. All right? Reason being, they're the furthest from the origin. Now, I'm not testing the 0.04. Here's my thought. If I have 5x plus 7y, since this point is 0, 4, 1 is bigger than the x-coordinate of 0, 5 is bigger than the y-coordinate of 4, 1 and 5 will give me a bigger values in here for x and y than 0, 4 would. And the same philosophy with 6, 3. This point's at 5, 0. 6 is bigger than the x-coordinate 5. 3 is bigger than the y-coordinate of 0. No reason to test these 2 points. These 2 are going to do better than those 2 points. So at 1, 5, 5 times 1 plus 7 times 5, 5 plus 35 is 40. Test the 6, 3, 5 times 6 is 30, 7 times 3 is 21. That adds up to be 51. So this point, 6, 3, is the point that's going to maximize my objective function. Now, if looking for the points furthest from the origin gives us the biggest value, then finding the points closest to the origin will find the min value. So we have the points 0, 2, 3, 0. Again, same philosophy. 0, 4, 0, 2. 2 is smaller than 4. 0, 0, that's a wash. This will give me a smaller value. 5, 0, 3, 0. 3 is smaller than 5. So I'm just going to test these 2 points because they're closer to the origin than that blue and red point were. So at 0, 2, we have 0 plus 14, 3, 0. We're at 15, 0. That's 15. So 0, 2 is the point that minimizes our objective function.